Welcome to the continuing video podcast series having to do with electrochemistry, oxidation reduction chemistry here at Ontario High School. This video podcast will specifically introduce Voltaic cells. Voltaic cells are also known as galvanic cells. It's a device that spontaneously transforms chemical energy into electrical energy. Transfer of electrons takes place through an external pathway. Cells typically contain two half cells which are physically separated and which contain a metal electrode immersed in an aqueous solution. And there's a word that you should be thinking about here because batteries are voltaic or galvanic cells. You are now looking at a wonderful diagram of a galvanic or voltaic cell, and what I would like for you to do is to copy this diagram down. This would be very helpful to you as we go through the rest of this podcast. And I think that the diagram itself is very self-explanatory. We'll get into what anodes and cathodes and all those kinds of things are as we go on. But please pause the podcast and write down this diagram, and that would be good. The half cells in a galvanic cell or voltaic cell have names. One of the half cells is known as the anode, and oxidation, which is the loss of electrons, takes place in the half cell known as the anode. In the diagram that you wrote down from the previous slide, the half cell containing the copper electrode is the anode. The half cell contains a copper electrode, which is solid, and an aqueous solution containing copper 2 salt dissolved in the solution, copper 2 being the Cu2 plus ion. The other half cell is known as the cathode. That's where reduction takes place. Reduction is the gain of electrons, and in the diagram on slide 3, the half cell containing the silver electrode immersed in a silver nitrate solution is the cathode. The salt bridge, very important. Voltaic cells use a salt bridge to complete the electrical circuit. As the oxidation and reduction reactions take place, ions from the half cell compartments migrate through the salt bridge to maintain the electrical neutrality of the solutions. Cations always move toward the cathode. Anions always move toward the anode. Cations are the positive ions. Anions are the negative ions. That last statement is one to ponder and remember. The beginning part of this podcast is going to be very heavy with terms that we haven't used before. So the next one has to do with electromotive force and the potential difference that exists between the two half cells, known as the electromotive force, pushes electrons through the external circuit flowing from the anode to the cathode. This cell potential, E sub cell, is measured in volts. So when you hear of something like an outlet, typically in America is 110 or 120 volts, it's a measure of the potential difference that exists in that outlet, and that is a measure of electromotive force. Reduction potentials. Reduction potential is the standard measure given to a half reaction when the half cell of interest is paired with a reference cell at standard conditions. The standard conditions are these. There are 1 mole per liter aqueous solutions, 1 atmosphere of pressure, and 25 degrees Celsius or 298 Kelvin. Now notice the difference here between when we worked with our gas laws. Standard temperature was always 273 Kelvin, which is 0 degrees Celsius. For reactions in electrochemistry, they have arbitrarily chosen 25 degrees Celsius, which is 298 Kelvin. It's very important when we get into calculations using the Nernst equation that you always use the Kelvin temperature, 298, rather than the Celsius. The reference half cell, when we look at these reduction potentials, is the standard hydrogen electrode. This is assigned a potential of 0.000 volts. All other reduction potentials are a comparison to this electrode. So at this electrode, the reaction is 2H plus 2 electrons forms hydrogen gas, H2. The E0, that superscript 0 there, means it's under standard conditions. The RED means it's a reduction reaction. In a reduction reaction, the electrons are added to the species and it reduces the amount of positive charge, and you can see that's what happened here. There are tables available that list the reduction potentials of most common half cells under standard conditions. We're going to use the reduction potentials for half reactions in order to build cells that produce spontaneous redox reactions, redox being short for oxidation reduction reactions. The half cell for the anode, where oxidation takes place, and the half cell for the cathode must be chosen so that when the reduction potentials are added, a positive E subcell results. And let me correct that. When I say that the reduction potentials are added, it's actually we're going to add the reduction potential of the cathode to the oxidation potential of the anode. And if you would correct that, that would be very helpful. So anyway, here we are. When we compare the reduction potentials, the more positive reduction potential means that the species has a greater tendency to be reduced. This half cell should be chosen as the cathode. The less positive reduction potential indicates that the half cell is best suitable for the anode. This is critical, and you may need to look at this slide for a little while before you move on. When we look at which half cell is going to be the cathode, which is going to be the anode, we want the one that has the standard reduction potential that has the more positive reduction potential. That's the one we'll choose to be the cathode. The less positive reduction potential we'll choose to be the anode. We need to arrange the half cell reactions so that the energy of the cell is positive. Here's how we're going to do it. We're going to reverse the less positive standard reduction potential reaction. When I say reverse that, what that means is instead of using it as a reduction potential, we're going to flip the equation so that the species is oxidized. When we do that, we're also going to flip the sign on the standard reduction potential, and when we do that, that will make it a standard oxidation potential. So the sign changes when we flip the equation. It is now a standard oxidation potential rather than a standard reduction potential, and this sounds like a lot of standard things, but you'll get used to it as we work through these problems. When we want to see what the energy of the cell will be, we'll add the standard oxidation potential to the standard reduction potential of the cathode. Remember, the standard oxidation potential is the half cell reaction that we flipped so that it would reflect oxidation occurring at the anode. If the energy of the cell is positive, the voltaic cell is arranged correctly. Let's do an example problem. We're going to build a voltaic cell using the following half cells and indicate which is the anode and which is the cathode, and calculate the E for the cell for the reaction under standard conditions. The two half reactions we have here are written initially as reduction reactions. You can see that the electrons are added on the reactant side, and the products have more negative charge or less positive charge than the reactants. So the two are aluminum 3 plus 3 electrons form aluminum metal, and you can see the standard reduction potential there is minus 1.66 volts. The other half cell is fluorine, F2, plus 2 electrons forms 2 fluoride ions. The standard reduction potential there is plus 2.87 volts. Now when we want to choose the half reaction that's going to occur at the anode, we want to choose the less positive reaction in terms of reduction potential, and it's real obvious here. Negative 1.66 is much less positive than positive 2.87. So aluminum is going to be oxidized at the anode. Well, let's solve this problem. We're going to flip the least positive reaction to become an oxidation half reaction rather than a reduction half reaction. So Al3 plus 3 electrons becoming Al becomes instead Al being oxidized to form Al3 plus 3 electrons. We flip the sign on the standard reduction potential when it becomes a standard oxidation potential. So it becomes a standard oxidation potential of plus 1.66 volts. We leave our reaction at the cathode, the reduction reaction, alone. Next, as with all reactions, we love to balance. We're going to balance the reactions so that an equal number of electrons are lost and gained in the half reactions. And one thing that's so important to note here, the oxidation and reduction potentials are not stoichiometric. What that means is that the coefficients in the balanced equation are not applied to the oxidation and reduction potentials. Those are what they are regardless of the stoichiometric coefficients used. So please remember that. Very, very important. We have 3 electrons in the oxidation reaction, 2 electrons in the reduction. When we want to get 3 and 2 to even out, we're going to take them both to 6. So we're going to multiply everything in the oxidation half reaction, the aluminum reaction, by 2, and everything in the reduction half reaction, the fluorine reaction, by 3. Once we've balanced the half reactions, and you can see them balanced here, we're going to cancel what's the same on both sides. In this case, the only thing that's the same on both sides are the number of electrons, and then we're going to add those reactions together as well as the standard oxidation potential and the standard reduction potential. So when we add these together, we get for the reaction 2Al plus 3F2 yields 2Al3 plus 6F minus. When we add the standard oxidation and reduction potentials together, 1 plus 1.66 volts plus 2.87 volts gives us a standard potential difference for this cell of positive 4.53 volts. There is an alternative method for finding the standard cell potential for a voltaic cell, and it does not require the flipping of one of the equations. For some people, flipping one of the equations becomes somewhat problematic, and this is a method for those who struggle with that. And so here's how we look at this. We examine the half reactions, and we still designate the least positive reduction potential as the anode half cell. So we're showing both the aluminum and the fluorine reactions as reduction reactions. If you'll notice, the aluminum is 2Al3 plus 6 electrons forms 2Al. But we call this the anode, and we keep their standard reduction potentials the same. Continuing on with the alternative method, what we're going to do now is subtract the standard reduction potential for the anode reaction from the standard reduction potential for the cathode reaction. So our standard reduction potential at the cathode is 2.87 volts. We're going to subtract the standard reduction potential for the species at the anode, which is minus 1.66 volts, negative 1.66 volts. So what we get is 2.87 volts minus a negative 1.66 volts. Of course, you know that subtracting a negative number ends up with a net positive change, so the 2.87 volts minus negative 1.66 volts equals positive 4.53 volts. You get the same value as the previous method that we looked at, but for some people this is a little simpler, and you should make a choice as to which one makes the most sense to you. The next 4 slides are for your benefit as you prepare for the AP Chemistry test. Substances that remove electrons from another reactant in an oxidation-reduction reaction. This is what an oxidizing agent is. The next several slides have oxidizing agents and their before and after states that should be memorized for the exam. As you move on, it would be best when you get to the next slide to pause the podcast and write these reactions down And then prepare flashcards. Do something, whatever you do that helps you to memorize a lot of information. This would be very helpful for you. This is the first of 2 slides that have oxidizing agents. These would be good to memorize. That's all I'm going to say about this. Pause the podcast and write these down, and again, do whatever you need to do to memorize these, because those that are successful on the exam, they know these. Be one of them. The last side of oxidizing agents that should be memorized, and again, their conditions. You see here the sulfuric acid when it's hot and concentrated. On the previous slide, you saw some acids that behave differently when they're concentrated and when they're dilute. Again, these are best memorized. Good luck with that. Pause the slide, write these down. Well, reducing agents. If oxidizing agents remove electrons from another reactant, reducing agents provide electrons or donate electrons to another reactant in an oxidation-reduction reaction. There are not near as many reducing agents that should be memorized for the test. These are them. So again, pause the podcast, write these down, and then whatever works best for you in terms of memorizing, go after that. You have probably never been so glad to be done with a podcast after writing down all those oxidizing agents and reducing agents. And so this is the end of the portion dealing with the Voltaic cell. Now, there are more podcasts to come dealing with calculations with Voltaic cells using the Nernst equation, and we'll get to those soon. But for right now, I'd like you to look at a quote from that inimitable British statesman Benjamin Disraeli. Characters do not change. Opinions alter, but characters are only developed. I wish you well.